Hello, this is the second video for the lesson on the movement of sun in sky and the stars at night. This is for class 8. So in the previous video, we have seen the angle of the noon sun on the summer solstice day at a latitude that is in the northern hemisphere. We looked at latitude 50 degrees. So using this diagram, we proved that the sun makes an angle of 27 degrees to the vertical. Vertical is the line which is perpendicular to the ground, and if you extend it, it goes. You can imagine it going to the center of the earth, and when you extend it outward, that is the point directly overhead of anyone who is standing at that spot. Okay, so the sun makes an angle of 27 degrees to the vertical at latitude 50 degrees, and on the winter solstice day, the sun makes an angle of 73 degrees to the vertical at the same latitude. Okay, there's this 50 degrees latitude. And we also saw that on the summer solstice day, the sun is directly overhead on all points on the latitude 23 degrees, which is the Tropic of Cancer. And on the winter solstice day, it is overhead, directly overhead on all points on the latitude 23 degrees south. It is Tropic of Capricorn. Okay, so this was for a high latitude, 50 degrees northern hemisphere. And now let's see. This is for a latitude 17 degrees. This is in the tropical zone. Okay, 17 degrees. 17 degrees happens to be the latitude for the city of Hyderabad in India. So very simple geometry. Again, you have the axis, north and south poles, the equator, and this black line here. This is the blue line is the latitude, 17 degrees. Okay, so here at this point, I have the radius, which is the vertical. So this is the vertical at that spot, and here you can see that according to this geometry, you can see that this angle is equal to 23 degrees minus the latitude, that is minus 17. So this angle here is 6 degrees. And so the sun makes an angle of 6 degrees, and it lies towards the north in summer. And in winter, at the same latitude, you look at the geometry here. Okay, so here the angles add up. This is 23 degrees and this is 17. So this blue angle is 40 degrees. So the sun makes an angle of 40 degrees to the vertical. So it lies a little low. So even though it is a tropical region, the sun is not high up on the head. It is slightly towards the horizon. So you have some, it feels a little cool. And this is about the direction of the sunrise. The first thing we saw in our lesson was we went out and observed the location where the sun rises. Okay, the spot where the sun rises, and it is not always in the east. So we saw that in winter the sun rises in the southeast, and in summer it rises in northeast. So this diagram explains why that happens. So this is on the left side, it is the summer. So the North Pole tilting towards the direction of the incoming sunlight. So this spot here, the maroon spot, it is about to have sunrise because it's moving from the dark shadow region, the night region of the globe towards the lighted region. So this is moving along this latitude, along this red line, because Earth is rotating. So you can see, so the east here is along the latitude, North is towards the North Pole. So the sunlight is coming in the direction of from northeastern direction in summer. And in winter, you can see the same latitude. Okay? So now this red spot is now on the other side of the globe. It's entering from the dark region towards the light region on the other side of the globe. And so east is again this way. So you can see that the sunlight is the sun's rays are coming in from the southeast in winter. So this explains what we saw, that the sun rises in the northeast in summer, and it rises in east in autumn on the equinox, and then it rises in the southeast in winter. So there is a north-south back and forth movement of the sunrise. And the difference in the angle is 40. The direction of the sunrise changes by 46 degrees between the two solstices. Okay, so now let's build a few models to show the path of the sun in the sky during the day. Okay, so if you stand at any spot on the earth, 3 different latitudes, you can see the horizon all around you. And how does the sun, where does the sun rise? How does it travel in the sky, and where does it set? So this is what we're going to see. So before that, let's just recap what we mean by the horizon. So we have seen that horizon is the piece of land, the circular spot of land that you can see from any place on the globe. So depending on your height, so this yellow pin, which is stuck vertically to the surface of the globe, that is a person. You can imagine that as a person. So depending on the height, so you can see a circle of land. Okay, so the light from your eyes, the light from these points on the circle, it reaches your eye, and beyond that you cannot see. And we have also seen that on the horizon, the directions are as follows. So if you take you have a longitude and a latitude passing through that center of that or where you stand, right? That's the center of the circle. So north is towards that longitude, towards the North Pole. South is along the longitude towards the north is along the longitude towards the North Pole. South is along the longitude towards the South Pole. East is along the latitude towards the east, and west is along the latitude towards the west. So this is what we have seen earlier. So let us look at this model for the path of the sun in the sky at latitude 50 degrees. So at latitude 50 degrees, on summer solstice, the day is very long. So the path of the sun is along a arc of a circle, which is more than half. The arc is larger than a semicircle. And the sun rises at noon, it makes an angle of 27 degrees to the vertical. And sorry. Okay, 27 degrees to the vertical. And on equinox day, it is the day and the night are of equal duration. So the sun it goes along an arc, which is a semicircle. And on winter solstice day, the night is much shorter than the day. So the arc is smaller than the semicircle. So let's look at the model that we have built. So this is the model. So this is the horizon. There's a person standing at that spot, and there are 4 directions, and there's the circle of land visible. So there are landmarks. So when you stand anywhere on any spot on Earth, you see some permanent landmarks, some hills, trees, which don't move. So you can use those um, to as reference to to locate the sunrise. Okay, so sometimes the sun rises behind this tree, sometimes it rises behind one of the hills, sometimes it rises behind the other hill. So depending on where you are, you have some important landmarks that you can use. So at 50 degrees latitude, this the first arc, which is this very long arc, is the path of sun at summer solstice. So sun rises in the northeast. So there it is. So so the bead represents the sun, rises in northeast, goes along that very large arc, okay, and at noon it makes an angle of 27 degrees and sets in uh, northwest, 23 degrees to west. And 23 degrees to the east, it rises, and 23 degrees to the west, it sets. And that is the vertical that, yeah, so and on the day of the equinox, yeah, sun rises. That is the arc for the equinox day, rises exactly in the east. And it goes up along that arc, which makes an angle of 50 degrees, same as the latitude. Okay, 50 degrees to the vertical. And sets in exactly west. So that is the only day of the year when sun rises exactly in the east and sets exactly in the west. And so it's a semicircle. So the day and night are equal on the equinox, both the equinoxes. The spring and the autumn equinox. And finally, on the winter solstice day, you have the small arc, a short day, and it's very inclined. It's lying at an angle of 73 degrees to the vertical. And it sets in uh, southwest, rises in southeast and sets in southwest. So this is very close to the horizon. The sun does not go up. So it is and it takes a very small arc, a short day. So this is the temperate zone. So in winter, you have a sun which does not go up in the sky and it's very mild. So that is why the weather is very cold. And summer, it goes up, still does not go directly overhead, but it goes up to the angle of 27 degrees to the vertical. So that is the warmest sun you can get. So it does not go overhead, even in summer, but that is the best you get. And this is the growing season. You have a long daytime and the sun is warm. So that is when all the crops grow. In winter, in temperate region, crops don't grow because the sun is very mild, the day is very short, and the weather is very cold. So next, let us look at the model for 17-degree latitude. This is the tropical region. So again, you have, so we already seen that the sun makes an angle of 6 degrees towards the north. And on both the equinoxes, the sun makes an angle 17 degrees, same as the latitude. And on winter solstice day, the sun makes an angle of 40 degrees. So just let us look at the model. So this is the model. So it has a in summer it has a larger arc because the day is long, and like at every other latitude, the sun rises in northeast in summer, so sets in south northwest. So, and on the equinox days, both the autumn and spring equinox days, so the sun makes an angle of 17 degrees uh, to the vertical. So it is close to being overhead, but not exactly overhead. And on some winter solstice, it makes an angle of 40 degrees. So it is closer to the horizon. So even though it is a tropical place, you still have the sun is little milder. So on the whole, the on the whole the sun is it moves from being from being hot to mild, slightly mild. So when it goes to this between these 2 points, so it's because on summer solstice day, excuse me please, so on the day of the summer solstice, it makes an angle of 6 degrees towards the north. Okay, and okay, so when it moves from the equinox, the spring equinox to summer, so it has exceeded at one point. It is directly overhead. So some time in May, before it reaches the summer solstice point, so there will be a day when the sun is exactly overhead at noon. Then on summer solstice, exactly on summer solstice day, it has gone little further. Yes, and then um, so again when it comes back from summer towards autumn, again it crosses that point where there is a day when the sun is directly overhead at noon. So there are 2 days in the year when the sun is directly overhead at noon and you don't have a shadow. So the shadow falls straight to your underneath your feet that day. Okay, so this is the model for the equator. So you have uh, the sun making an angle of 23 degrees towards the north. The north it leans towards the north in summer, and it leans to 23 degrees towards the south in winter, and it's directly overhead on the equinox days at noon, that is. So this is the model. Okay, so there's an arc leaning towards the north. This is north. Uh, and there's the other arc leaning towards the south. So that is winter. The arc leaning towards the north is the summer. And then arc which is directly overhead, that is on both of the equinox days. So that is and all these arcs are of equal, they're all semicircles. There's a slight mistake in the model. So one of the arc looks a little larger than the others. They should all be perfect semicircles. The same as, okay. So because at the equator, the length of the day and night is the same throughout the year. So these are the 3 models. And Now let's see what happens at the North Pole. If you reach the North Pole, what happens? How does the sun's path look? So I'm showing you. Okay. So at North Pole, the sun rises slowly after spring, and it is it is it lingers near the horizon. It goes round and round the horizon, slowly starts rising up. So by summer solstice, it has risen up 23 degrees in to the horizon, and then slowly, as as autumn approaches, again it goes down, and by winter, by autumn equinox, it is again back on the horizon, and it goes down and stays down throughout winter. So that is how the sun's path looks like at North Pole. Okay, so now that we've seen the models, let's move on. So let's just point out that on the equinox days, the noon sun makes an angle with the vertical, which is equal to the latitude angle everywhere on the earth. So if you're at 40-degree latitude, then the sun makes an angle of 40 degrees with the vertical. Okay, now after having seen the path of the sun in the sky at different times of the year and different latitudes, so let's just go back to shadows once again. So we saw how the shadow behaves on one single day, randomly on any day of the year. We saw how the shadow behaves. So it's long. We start with long shadows, which are pointing towards the west, and the shadow becomes short. The shortest shadow lies along the north-south direction, and in the evening, the shadows are long again, and they point towards the east. Okay. So, okay. So what we did last time was used magnetic compass to check that the shortest shadow lies along the north-south direction. That is actually not accurate, because the magnetic north pole and the geographic north pole related to the spinning of the earth, they are not the same exactly. So there's a difference. So now let's see what happens when we use the globe, fix a pin on the globe. So just like we used a pillar or a pole, and see how the shadow behaves. So this is the globe and has stuck pins here vertically to the surface of the globe. So this is the pole whose shadow you want to look at. And this the torch light coming out of this mobile phone is going to be the sun. So as the earth rotates, let's see what happens to the shadows of these pins. One is stuck on, so they're both stuck on the same longitude. One is on equator and the other is around 40 degrees latitude. Okay, but they are all both being stuck on the same longitude. So that means they both will experience noon at the same moment, because they are on the same longitude. So all points along the longitude will come directly, will face the sun and have noon at the same point. Okay. They are along the same longitude. That's what I'm trying to show you there. Okay. So now let's see what happens when one is on the equator, one pin is on the equator, and the other one is at 40 degrees latitude. Okay, now that I have switched off the light, so let's see, rotate the globe and watch the shadows. Okay. So here's the sunrise. Okay, you have long shadow. So this is a long shadow at sunrise. You can at equator you can see it clearly. At 40 degrees, it's not very clear. So as the Earth rotates, the shadow becomes smaller, okay? And it moves towards north. And then, okay, so the shortest shadow that you get, this is the shortest shadow, and it is along the shortest shadow is along that longitude line. So it is pointing directly towards the North Pole. So the same thing is true for the other latitude. Although it's not clearly visible, the same thing happens. So as you rotate it, so this is noon. So this is the exact noon shadow pointing along the okay. So this is okay. So this is not the equinox day. So the shadow does not disappear. Even at equator, you do have a shadow, and that is the shadow, and it is pointing towards the north. This is north side south direction along the longitude line. So that is what we need to observe. So what do we know now? We know that to find the north-south direction at any spot, all you need to do is fix a vertical pole and observe the shortest shadow that it casts on any day of the year. So that will point along north and south. And the perpendicular to that, if you draw a perpendicular, you can find the east and west, the true east and true west. East is not the place where the sun rises on any day of the year. East is the day only, the sun rises only on the equinox days. So the ancients would observe the equinoxes and to find out the true east and the true west. And they would use the shadows to find the true north and true south. So these cardinal directions were very important to the ancients. So they had a lot of religious importance and about this. And all the ancient monuments have used this cardinal directions. So they were well versed in finding these directions. So all over the world, you find ancient monuments which are oriented along these directions. Okay, so lastly, can we use shadows to tell time? Okay, so in the old days, time was local. So now we have international time, and so but back then the notion of time was local. So when the noon happens, when the sun goes high up, that is noon, and between the noon and the next noon is one day, and that they wanted to divide that into equal intervals of time. Okay? So you can use shadows, but we've seen that the shadow of a vertical object changes from day to day because the path of the sun is not the same. The arcs are different. Every day the arc of the sun's path changes little in the sky. So depending on where the sun is, the length of the shadow will change. So that means the shadow pattern does not repeat itself, okay, from day to day. But there is a device called the sundial, which allows you to tell the time using the shadow on any day of the year. So I will just give you how the sundial is constructed. You should try and find out how it actually works. Okay? So I'm not discussing why this works. That I will leave that to you. So the sundial consists of this triangle, which is fixed in the vertically to this wooden base is horizontal, and this triangle is fixed to it in the vertical plane. So this is a right angle triangle. This angle C here has the same magnitude as the latitude. So depending on where you want to use this sundial, you need to set the angle C to that same angle as the latitude. And then place this device in the open where sunlight is available, and place it such that this base BC lies along the north-south line. So by observing the shadows, we know how to find the north-south line. So place it along the north-south direction, and then you can calibrate it. Okay, so starting around 7 o'clock in the morning, when the shadow is distinct, you can trace the shadow, draw it at each hour, at 7, at 8, and so on. So you will have, the shadow will fall on one side, and then so afternoon the shadow will switch over. It will fall on the other side of the triangular, the triangle, the plane, right? The triangular plane. So when you draw these shadows, these maroon lines here, which are slanting, these are the shadows. Okay, so you mark the shadows throughout the day on any day, okay? And then you can mark the time at which that shadow was traced, and you can use that. So once you calibrate it like this, so calibration is setting any device, right? The markings of any device against some standard. So you use a standard watch and then set and mark these shadows every 1 hour, and then you have calibrated it. Okay, so that gives you the time. Okay, so you can use this device throughout the year. Okay, so the shadow does not disappear. Sorry, this. So when the shadow is shortest, it is the local noon. So it is noon at that place where you're observing. Yes, but our times that we use, the standard Indian standard time or the standard time of any country is according to some standard longitude. So in India, for example, the Indian standard time is defined for the longitude 86.5 degrees east. This is the longitude which runs through the middle of the country, almost approximately to the middle of the country. So when it is noon at that longitude, then we take it as 12 noon IST. So rest of the country also follows that as noon, even though it is not their local noon. The sun is not at the highest position in the sky at 12 noon IST. Okay, so in places in India which are to the extreme east or to the extreme west, it is either past noon or before noon. So there is this local time, and local time is what was used for a very long time. So now let's stop with this. Now we have understood the path of the sun in the sky in all seasons and at all latitudes. Okay, so now let's see this night sky. So in the night sky, we see stars. So do the stars also move? What is the manner in which they move? So does their movement change according to seasons? Does the movement change according to the latitude on Earth? We'll see that in the next video. So now we will stop with this.